Welcome to this important topic of Fourier series. My name is Kannan Modgalya. We will derive Fourier series. We will also arrive at the Fourier series pair. Let us consider a continuous time periodic signal with a period Tp equals 1 over f naught. It has a Fourier series of the following form: Ck, a constant yet to be determined, times exponential j 2 pi k f naught t, this k running from minus infinity to plus infinity. It is easy to show that this representation gives a periodic signal. We want to calculate Ck. To do that, we will multiply both sides of this equation by this exponential term, and we will integrate from t0 to Tp, where Tp is 1 over f naught as given here. So let us integrate the left hand side. I have multiplied u of t by this exponential term given here, and we are integrating from t0 to t0 plus capital Tp. This L is an integer, this k is an integer, and so on. So let us do it on the right hand side also. Okay, I have taken this summation multiplied by this exponential term, integrating it with respect to t from t0 to t0 plus capital Tp. So let us start with this and simplify it in the next slide. Okay. The right hand side can be written as follows if there is no difficulty in summing this expression. Whenever you have infinite number of terms, you have to worry about the existence of this sum. In all the things that we will see in this course, we will have finite sum, so it is possible for us to exchange summation and integration. So I am integrating first and then summing up. Remember, however, if this sum does not exist, if the left hand side does not exist, you cannot write the right hand side, especially if this converges. In other words, supposing this does not converge, and through clever mathematical arguments you can write it like this, and it converges, then your mathematical arguments are not at all acceptable. So here we assume that these two are okay, we can exchange the integral sign and summation sign. What I will do now is I will evaluate this first for when k is equal to L, this becomes 0, this whole thing becomes 1. So integral dt, and when it is integrated you get Tp. So it becomes CL/Tp here, that corresponds to k equals L. We need to consider all other terms which I write here. K goes from minus infinity to plus infinity except when k is equal to L. When k is not equal to L, this is not 0, so I can integrate this. When I integrate this, the exponent comes to the denominator here, and we take the limits as t0 to t0 plus capital Tp. So let us simplify this. When I integrated this, I obtained this expression in the previous slide, and k is not equal to L, so k minus L is not equal to 0, we let n equals k minus L. So let us evaluate this second term. So this is the second term, only the numerator part, and let us substitute first t0 plus capital Tp. In the place of t, I have substituted t0 plus capital Tp minus the term corresponding to small t0. So I have got this. Now you can see that some simplification is possible. f naught t naught is a common factor, I pull this out. Then when I multiply this by Tp, notice that f naught is the reciprocal of Tp. So f naught Tp become 1. So I get j into 2 pi n, which is what I have here. So that comes from this Tp term here, and this term corresponds to this 1 here. I have factored this out. And you can see that this is equal to 0 because this is equal to 1. As a result, this whole term becomes equal to 0. So I can get CL directly, take this Tp to this side, 1 over Tp times this expression, I write it, and this integral goes from small t0 to t0 plus capital Tp. Because this signal u is periodic, I can choose any arbitrary period Tp. So I get this expression. We call these two expressions as a Fourier series pair. This is our periodic signal. It is given in terms of the Ck, and this Ck is evaluated using this ut. This integral is over an arbitrary period Tp. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.